Now the third situation can be when they are unknown, okay, but they are unequal. So sigma 1 square is not equal to sigma 2 square, but it is unknown to you. So before going into that, we need to see two lemmas which would be helpful in finding out and proving the results later on. So the first lemma over here says that if you have a sequence of random variables, then the variance of the sample variance, okay, so sample S square is your sample variance, this would be twice of sigma raised to the power 4 divided by n minus 1. So let us see how we can prove this. Here what we are doing is, we have to prove basically that variance of S square will be twice of sigma raised to the power 4 over n minus 1. Recall that in the last week, what we have seen is that n minus 1 times S square over sigma square follows chi-square distribution with n minus 1 degrees of freedom. Okay. Now if you suppose this as u, that u is this random variable, so if u follows chi-square with n minus 1 degrees of freedom, then we know that for chi-square, expectation of u would be same as the degrees of freedom, but the variance of this chi-square is twice of n degrees of freedom. Okay. Now let us find out variance of u. When you find out variance of u, it means that if you are finding out, let us substitute the value over here. So n minus 1 times S square over sigma square. This has to come out as twice of n minus 1 by this logic, right? Now let us try to simplify this left hand side. N minus 1 and sigma square, these are constants, and we know that variance of ax, if x is a random variable, this would be a square times variance of x. So n minus 1 s square over sigma raised to the power 4, variance of s square would be twice of n minus 1. Now n minus 1 and n minus 1 would cancel out. Okay. So variance of s square, that is sample variance, is nothing but twice of sigma raised to the power 4 and n minus 1. So this is what we wanted to prove. Okay. So this is our first lemma. Now we will move on to the second lemma. So now we come to our second lemma, which says that beta hat times of sigma 1 square over n1. So this quantity over here, this is going to follow your chi-square distribution with these many degrees of freedom, which is defined in this way. So now let us see what does it mean. Here we are basically going to use this approximation which says that if you have beta times this quantity over here, then it would follow chi-square with beta degrees of freedom. Okay, so if you just look at this, this is basically inverse is there, so you can take it in the denominator also, right? Now if you have, suppose we denote this random variable by v. Okay, if we denote this by v, then it shows that if v is following chi-square distribution with beta degrees of freedom, then what will happen to the variance? Variance of v will be twice of beta, as we have seen this now. So let us apply this variance term on this v. Okay. So if you see over here, so we have defined v as this, right? And if v follows this, then you would expect that variance of this quantity would be same as variance of this, right? So basically we are trying to prove variance of v is twice beta, right? Now before finding out variance of v, you can see from these steps that instead of v, you can just substitute this value, that is beta, this thing over here, right? This is what we have defined as v just now. Now if you see, Here beta is a constant that would go outside the variance, so it will become square. Okay. So this term over here, this is square. Now similarly, this inverse term over here, this is also a constant, so this will become square, because variance of ax plus b, suppose if we have, then it would be a square times variance of x. Right? And now you are left with variance of, so you have variance of s1 square over n1 plus s2 square over n2. Okay, you can take variance inside because these two are independent. So here it would be variance of s1 square over n1 square plus variance of s2 square over n2 square. Right? So same thing you are getting over here. Fine. Now we have just now seen in your first lemma what is variance of sample variance, right? S square. So that is basically, so variance of S square, variance of S square, we have just now seen that it would be twice sigma raised to power 4 over n minus 1. So for S1 square it will be sigma 1 and here you will have n1, right? And for S2 square you would have, so all the ones will be replaced by 2's. So here you see that we are writing n1 square is already there, so this quantity over here, this is basically variance of S1 square and this is the variance of S2 square. Okay? Which is not written over here. Fine. So let me just clean it up a bit so that I can explain it further. Here if you see, this beta would cancel out with this one, right? So you will have this side, one beta would be there, and these 2's would get cancelled from this 2. So if you have to find out beta, so you can take this term on the left hand side, so beta would be, so here you will have sigma 1 square by n1 plus sigma 2 square by n2 whole square divided by this term would come in the denominator, right? So this would be sigma 1 raised to the power 4, n1 minus 1, n2 square, n1 square, sorry, plus sigma 2 raised to the power 4 over n2 minus 1, n2 square. Same thing can be seen from here, that if you solve this, you can see that this is what I have written, sigma 1 square by n1, the numerator is same and the denominator you get this. Okay. Now since these two variances are unknown to us, it means that we have to replace it with their corresponding estimates. So we know that we can estimate your population variance with your sample variance. So instead of this, everywhere you are replacing sigma 1 square by s1 square and sigma 2 square by s2 square. So here you get s1 square over n1 plus s2 square over n2 and likewise. Okay. And you also see that this basically beta hat times of this is following your chi-square distribution with beta hat degrees of freedom. So you are replacing basically the approximation that you had earlier. So in that you are replacing beta with the estimate of beta, that is beta hat. Okay. So now this is the result that we have, and we will now use it to prove our next theorem, which says that if the two variances are unequal, that is sigma 1 square is not equal to sigma 2 square, but both are unknown to us, right? The moment we see unknown, it should click to you that sample variances will come into picture and the distribution would no longer be following your normal distribution, but rather it would be replaced by t distribution with certain degrees of freedom, as we have seen for these single sample problems also. So here we are looking at two sample problems, and likewise it could be generalized it for more number of samples as well. Okay. So if you are given this information that independent samples of size n1 and n2 are drawn from two populations with means mu1 and mu2, and their corresponding standard deviations are x1 square and x2 square, then this quantity over here, this is going to follow t distribution with beta degrees of freedom, beta hat, where beta hat is what we have just defined in the lemma. Okay, the same thing is coming here. Now in order to prove this, let us first denote this term as t. Some t is this random variable. Whenever you have to prove that a random variable, the distribution of a random variable is t, we know that how the t distribution can be generated. T distribution arises basically if you have a standard normal variate, okay, and you have another random variable which is following chi-square with suppose r degrees of freedom, then t basically if you define z over square root of v by r, then this would follow t distribution with r degrees of freedom. This is the common understanding that we have. Now we are given the random variable t in this form. So we would like to rewrite it such that we get a term in this way, that in the numerator you have the standard normal variable, whereas in the denominator you have a chi-square random variable with these degrees of freedom. And if we are able to write this random variable over here in this form, then our job will be done. Okay, so let us see how do we prove that. So we begin with this t over here. Okay, so this is t. This is the same thing that we already have just now. We have seen this is the one that we are interested in, and we have, you see over here, we have multiplied and divided by the same quantity over here. Okay, so it does not impact the original term that we had. Now if you rearrange the terms, what you can see from here, that this sigma 1 square over n1, so this one over here, one can come in the denominator and you can write it as divided by under root of this term, right? So this is one and the same thing. Okay. Now we know from the first result that this is going to follow your standard normal distribution, because in the first place we have seen that x1 bar minus x2 bar, this would be following normal. The means would be mu1 minus mu2, and variance would be sigma 1 square over n1 plus sigma 2 square by n2. And when you standardize it, this would basically be the same thing, that is z over here. Right? This minus mu1 minus mu2 and divided by square root. Okay? So this is your standard normal variate. Okay? You need to add over here. Now we have to focus on this part. So we have got a standard normal variate as we wanted over here. Right? So this thing is done. We are interested in this chi-square now. So let us see how we can obtain that. In order to obtain for chi-square, if you focus on this term over here, we have, this is basically what? You can write it. So square root of these two, this is basically, you can write, you can take this as the inverse in the numerator, like this, right? And you are multiplying and dividing by beta hat. And if you can recall, we have from the second lemma, this term is basically, we are denoting it by v, and we are dividing it by the corresponding degrees of freedom. Because from the second lemma, it said that v, if v is this quantity, it will follow chi-square with beta hat degrees of freedom that we have defined in the first slide of this theorem. So basically now what we have is that z is already there, if you see, This is standard normal variate over here, this part. Let me use some other color over here. So this thing over here, this is your standard normal variate, Z, and you have divided by this quantity over here, which is basically your chi-square with beta hat degrees of freedom. This basically proves your result. Okay. Now, note that usually whenever sigma 1 and sigma 2 are unknown, we estimate them using S1 and S2, their corresponding sample variances or the sample standard deviations as we have done earlier. Now, if your S1 over S2 is between 0.5 to 2, right, then you can assume that the two variances are equal. So this is basically a rule of thumb, and we say that if it is following this criteria, then we can assume that sigma 1 square and sigma 2 square, these are approximately same. And if that is the case, then instead of dealing with separate standard deviations or standard sample, these one S1 square and S2 square separately, you can estimate the common variance sigma square using pooled standard deviation. And pooled standard deviation basically nothing but, you can see that it is the weighted average of the individual sample variances. Okay, so you have S1 square and S2 square. Now in cases where you can find that, okay, this is happening, that is sigma 1 square is nearly same as sigma 2 square, then instead of dealing with them separately, you can just directly assume that they are same as sigma square, and you can estimate it with this pooled sample variance, which is basically this pooled sample variance, which is this. So S1 square and S2 square. We know that for both of them we have these as the corresponding degrees of freedom, right? So we are giving these as the weights, and for this one we have N2 minus 1 S2, right? Because sample variance follow chi-square with n minus 1 degrees of freedom. So with that same logic, your pooled standard deviation could be very well defined as n1 minus 1 S square, right? So weighted average in this way. Because weighted average is what? If your weights are suppose W1 and W2 and your random variables are X1 and X2, so weighted average would be W1 X1 plus W2 X2 divided by the total weight. In this case, the total weight would be N1 minus 1 plus N2 minus 1, which is essentially N1 plus N2 minus 2. Okay, so the same thing we are using. This is basically your weighted average. Now with this, you can again find the proof for this. In this situation, we assume that the two variances are equal and sigma square is unknown to us. If sigma square is unknown and these are equal, which means that first of all sample variance will come into picture, but instead of dealing with them as individual sample variances, we can also use your pooled sample variance. Okay, that is SP. So if you have independent samples of size N1 and N2 coming from a population with means mu1 and mu2 and variances as S1 square and S2 square, then you can see that this quantity over here, this would follow T distribution with N1 plus N2 minus 2 degrees of freedom. Now again, as we have seen in the previous example, again a T distribution can be obtained if you have a standard normal variate and a chi-square random variable. Right? So let us denote this term over here as T, okay, and try to rewrite it such that we get a standard normal variate and divided by square root of this thing. Okay. So in order to prove this, we can see that T is this. Okay. x1 bar minus x2 bar minus mu1 minus mu2 SP, that is pooled standard deviation 1 over n1 plus 1 over n2. Now you can substitute the value of the pooled standard deviation. Okay, that is square root of n1 weighted average of these. And here what we are doing, we are multiplying and dividing by sigma. Okay, because we need to rearrange the terms. Fine. Now what we can do is that we can take this sigma and this term over here. Okay, so this can still remain in the denominator, and we would write divided by this term over here, and this entire thing that we have. This thing that we have, it can also be written as divided, and this thing comes over here. Okay, into 1 over n1 plus same thing. Okay, as it is we have done over here. Here you can see that we get 1 sigma square in this one. So we try to utilize the information that we have gained so far, because we know that n1 minus 1 s1 square by sigma square is going to follow chi square with n1 minus 1 degrees of freedom. So since we just now have n1 minus 1 s square, and we need to have an extra term in the denominator, we need to multiply and divide by sigma. Okay, so now when you rearrange the terms, you would get sigma square and sigma square on both the sides, and this one would be total degrees of freedom. Okay, you can see it more clearly now. Okay. Now if you look over here, this is the term which is basically your standard normal variate, right? Again, which is coming from your second theorem, where sigma 1 square and sigma 2 square is same as sigma. They are known, but this is it. In that case, your normal distribution would be there, but sigma times of this would be there. Okay. So the second result said that x1 bar minus x2 bar follows normal with mean mu1 minus mu2 and sigma square root of, you can have, because if you are writing a standard deviation, so let me just write the variance only. So it would be simply sigma square 1 over n1 plus 1 over n2. So since this is the variance, when you take the standard error, it would be sigma times square root of this one. Now if you look at this side, what is happening? We have seen that this is a chi-square random variable, this is also a chi-square random variable, and if you have two chi-square random variables which are independent, then their sum would also be chi-square again, and their degrees of freedom would be added. Okay, so here this would following, suppose this is u1, so this one would be following chi-square with n1 minus 1 degrees of freedom, and if this is u2, this would be following chi-square with n2 minus 1 degrees of freedom. So u1 plus u is u1 plus u2. This one would be following chi-square with n1 plus n2 minus 2 degrees of freedom. Okay, so let us see that. So we know that Z is this, and U will follow this distribution because individually these two are independent, and it is one is chi-square n minus 1 and the other one is chi-square n minus 2. So now you have in the numerator is Z, and in the denominator you have U divided by the corresponding degrees of freedom. So it will follow the distribution with n1 plus n2 minus 2 degrees of freedom. If you have to find out the pooled standard deviation, then suppose it is given that the quality of light bulbs manufactured by a company in two separate facilities, plant A and plant B, and a testing procedure is carried out. The recorded data includes the lifetime of the bulbs. Okay, So these are given to the planting and planting. If you have to find out the pooled standard deviation, that is SP, you need to first check whether their corresponding sample variances are same or not, right? So you have S1 square and S2 square. From this data set, you can find S1 square for this one corresponding to this one, and S2 square would correspond to this one, right? Now if you find out that S1 square over S2 square falls somewhere between 0.5 and 2, then you can assume that the two population variances were approximately same. And instead of using in the separate S1 square and S2 square, you can just use this SP square. That is pooled standard, pooled variance, sample variance. Okay. So in this, if you see over here, the sample mean, so you can calculate these values. So sample mean comes out to be 2.39 and variance come out to be this. Similarly, when you calculate the standard deviation, it comes out to be this. And here you see that their ratio is nothing but it is 0.909. So in this case, since their ratio is between 0.5 and 2, you can say that we can use the two variances are nearly equal, and we can use our last theorem which says that SP square pooled variance would be this. Okay, so we have seen basically 4 different cases where we are focusing on the difference of sample means, and we mainly emphasized on whether the two samples that have been taken are independent. Okay, so we have seen situations when variances are equal, known to us, or unknown. Likewise, if they are unequal, then what is the situation? So we have seen 4 different cases.